This is a video to help you understand that a current carrying conductor which is placed in a magnetic field experiences a force. And we also are going to see what the magnitude of the force experienced by a current carrying conductor placed in a magnetic field will be. Now we know that a moving charge in a magnetic field experiences a force. So current flowing in a conductor is nothing but movement of charges inside the conductor. So all of those moving charges, since they are moving in the magnetic field, will experience some force. And thereby the whole of this current carrying conductor, therefore, when placed in a magnetic field, experiences a force, the direction of which is given by Fleming's left-hand rule. It tells us that we need to stretch the thumb, the forefinger, and the middle finger, of course, of our left hand, mutually perpendicular to each other, like this first. Then, if the forefinger points in the direction of the magnetic field, the middle finger points in the direction of the current, then the thumb will point in the direction of the force acting. Remember, the word if here is very important. If the forefinger points in the direction of the magnetic field and middle finger points in the direction of the current, then the thumb points in the direction of the force. So if is very important here. You need to understand that clearly. Just to make it easier for you to remember this statement, you can think of FBI, the Federal Bureau of Investigation, of course in the US. So F is your thumb, F means force, B is your forefinger, B means magnetic field, and I is your current. So F, B, I. Remember that. Let us try applying Fleming's left-hand rule to this scenario given in here. So we have a conductor over here, say for example a wire carrying current I in the upward direction, and we have a magnetic field depicted by these crosses over here. And what do these crosses tell us about the direction of the magnetic field? It tells us that the direction of the magnetic field is perpendicular to the plane of the paper but going inward. So the direction of the magnetic field is perpendicularly going into the plane of the paper. So applying Fleming's left-hand rule here, the forefinger is pointing in the direction of the magnetic field, the middle finger is pointing in the direction of the current, then the thumb points in the direction of the force acting. So to say, the force acting on this current carrying conductor placed in this magnetic field is towards our left-hand side. Let us now see what will be the magnitude of this force acting. So if L be the length of the conductor in the magnetic field, so L is this length present in the magnetic field, A is the cross-sectional area of the wire or the conductor, don't forget it's a circular cross-section, and small n be the number of charges. Now charges basically are electrons, so number of charges or electrons per unit volume of this conductor. So if this much is unit volume, it's a 3D picture, don't forget, then the number of electrons or number of charges in this unit volume is small n. Therefore, the total number of charges in the conductor, capital N, will be equal to small n into the volume of the conductor, AL. So the force experienced by each charge moving in the magnetic field, of course, with say a velocity v, is given by F dash. So F dash is equal to EV cross B, which can be written as EVB sine theta. Therefore, if this is the force experienced by a single charge, then the force experienced by the total number of charges, capital N, inside the conductor will be F, which will be equal to N into F dash. So this comes out to be equal to small n AL, because this is the total number of electrons, which is equal to capital N. So NAL into EVB sine theta. Now NEAV is equal to current. We have seen the relation between current and drift velocity inside a conductor. So NEAV is equal to I. So this thing can be written as ILB sine theta. So therefore the force experienced by the total number of charges inside the conductor is given by IL cross B. Now since the force experienced by the total number of charges inside the conductor is the same as the force experienced by the conductor itself. Therefore, the force experienced by a current carrying conductor placed in a magnetic field is given by F, which is equal to I L cross B.